We've briefly seen how ODE eigenvalue problems might arise when we consider the guitar string. We're now going to look at how we can use the shooting method to solve them. So, the equation for the mode shape in our guitar string is given by d squared y dx squared is equal to negative lambda squared y, where the lambda squared are eigenvalues. If we want to try and solve this equation using some kind of ODE integrator, we're going to need to split that equation into two first order ODEs. So let's let dy1 dx equal to y2, and dy2 dx therefore is equal to negative lambda squared where y1, where y1 is equal to big Y. So what are the boundary conditions that we know? Well, y1 of 0 is equal to 0, and y1 of L is equal to 0. We're given those conditions. If we want to integrate these two equations, we'd need to start, for example, on the left-hand side, and we'd need to know what the boundary condition on y2 was equal to in order to be able to start the integration. So what are the boundary conditions on y2? Well, in actual fact, they're unknown. We don't know what the slope of the string is at either endpoint. Also, in order to integrate this equation here, we need to know something about the eigenvalues lambda, or lambda squared. What are they? Well, they're unknown as well. So we've got a couple of things that we do know, but we've got a couple of important things that we don't know. How can we start integrating? We're going to have to deal with a rather subtle point here, so I'll try and explain this slowly, but you may need to come and see me if it doesn't sink in. So first, we're just rewriting our ODE here. Note that if y of x is a solution to this ODE, then so is alpha times y of x. So in other words, if we replace y here by alpha y, let's just write an alpha in here, we can see that we can divide the alpha straight back out. Okay, that's provided alpha is a constant. So, alpha yx is also a solution if y of x is a solution. What that means is we can multiply or scale our solution by a constant and it's still a solution. If we scale our solution by alpha, what's the derivative of the scaled solution? Well, it's just equal to alpha times y dashed. So what this means is if we choose a particular slope, it's a little bit like specifying the parameter alpha. So if we put 1 and 2 together, what that means is we can choose any value for the derivative at the endpoints, and the solution that comes out is going to be a solution of the equation. If we choose a different derivative, effectively, we're choosing a different value of alpha here. So, we're still going to get a solution provided these two boundary conditions are satisfied. It doesn't matter what the initial slope is equal to. Now this argument relies completely on our boundary conditions being homogeneous, in other words 0. If that's not the case, then we can't do this. But they are 0, so let's continue. So what that means is, if the red solid line is a solution, we scale it, for example, by a scale factor of 1/2. That means the slope at the left-hand point is 1/2, and the solution has the same shape, but half the amplitude. If we choose a slope that's twice as big at the left-hand boundary, we can see that the amplitude of our solution will be twice as big, but it's still a solution, and it still satisfies the boundary conditions at both points. So, changing y dash to 0 only changes the amplitude of our solution. It doesn't change the underlying form. So therefore, when it comes to integrating, we can choose any value we like for y dashed of 0, except of course for 0. That will just give us a straight line. What this also means then is that y dashed of 0 is not the adjustable parameter we seek to find. So we need some other unknown to be our adjustable parameter. So the boundary conditions at the left-hand side we need to use to start the integration are y of 0 is equal to 0, and y dashed of 0 is equal to some constant which is non-zero. The constraint that we aim to achieve is once we integrate our solution from the left-hand side to the right-hand side, or from x is equal to 0 to x is equal to L, we want to have our solution y of L being equal to 0. That's the constraint we've got. Once we've started with these two conditions that y is equal to x is equal to 0, we want this to be satisfied when x is equal to L. 0 is the value our solution must satisfy when we integrate to x as L. So therefore the adjustable parameter can only be lambda, or perhaps lambda squared. It doesn't matter whether we treat lambda or lambda squared as the parameter, we end up with the same result. So the eigenvalue is the parameter we must find to satisfy the constraint y of L is equal to 0. Unlike our previous looks at boundary value problems, there is more than one value of lambda that satisfies this constraint, and we'll see that in a minute. This, of course, however, adds complexity to our algorithm. So the problem is a little bit like a standard boundary value problem, but we need to choose suitable values of lambda. Now, one of the things that is very useful to do here is to plot the predicted value of y at x is equal to L for a range of lambda. That will help us understand what we're looking for. So for example, in this problem here, if we integrate from x is equal to 0 to x is equal to L, and we see what the value at x is equal to L is equal to, it's plotted in that blue curve there. And this is our chosen value of lambda. These are not eigenvalues yet, remember, this is just choosing arbitrary values of lambda. Our constraint is that y of x is equal to L is equal to 0. That's represented by that red line there. Therefore, where the blue curve hits the red line, those are our eigenvalues. And, as we can see, there are multiple values of lambda that satisfy the constraint. And in actual fact, for most eigenvalue problems, there are an infinite number of eigenvalues. Like other boundary value problems, we need to use a root finding method to find each of our lambdas. The function we're finding the root of is a function of lambda and is the solution of the ODE at x is equal to L. Bisection or secant are the most useful techniques here, especially seeing as we're trying to find multiple examples. Once we've found our set of eigenvalues, lambda j, and let's imagine we're only going to calculate n of them, we then need to solve our ODE for the eigenfunctions. So there will be a separate eigenfunction for each different eigenvalue. So the eigenfunctions we're going to call yj. And the way we do that, of course, is to just use the lambda j that we found and the ODE solver that we would like to use. ODE 45, or perhaps one that you've written yourself. This then completes the ODE eigenvalue problem. For our particular problem here, d squared y dx squared is equal to negative lambda squared y, the eigenfunctions are y of j is equal to sine j pi x divided by L. And they look like those functions in the graph there. So that's the eigenfunction for j is equal to 1, j is equal to 2, j is equal to 3, j is equal to 4, and so on. So assuming that we have an ODE for a variable u, so I'm just now going to summarize what we need to do for the algorithm, and say it's defined on some domain, x goes from 0 to L, with some unknown eigenvalues and known boundary conditions, u0 is equal to u0 and u of L is equal to ul. The algorithm for determining eigenvalues and eigensolutions is as follows. Choose a range of values that we want to investigate for lambda, so that they lie between lambda min and lambda max. For n different values across this range, integrate the ODE with lambda I from x is equal to 0 to x is equal to L. Calculate the value of the solution at x is equal to L. We're going to call that UL. plot U of L as a function of lambda. Now you don't have to do this step, but it's a really sensible thing to do, to see whether you've actually captured any eigenvalues or whether you've perhaps captured too many. Then use a root finding method to find which values of lambda give us that the U that we want at the left-hand side is, the U that we calculate at x is equal to L is actually equal to UL that we want at this point. And once we've found those values of lambda, those are the eigenvalues. Then for each of those eigenvalues, solve the ODE to get the eigenfunction.